Okay, well today we'd like to talk about fixed axis rotation, and we're going to start off talking about rotation about the center of gravity. Remember, we're in rigid bodies now. We have shape and we have mass, so there's a moment of inertia that we have to deal with. We haven't talked about that much yet, but let's suggest that there's a shape here that is being accelerated in the angular way by some moment, and it's going to have some resulting alpha, or it could have a different kind of shape and may have a force times a distance. The same kind of thing, same kind of analysis applies, whether the moment is being supplied by a torque of some sort, or whether it's a force times a distance. In either case, an alpha will be the result. And so our moment equation suggests that the sum of the moments about our center of gravity is equal to the mass moment of inertia about the center of gravity, or of the center of gravity, times alpha. Okay, so first of all, that's the only equation that we're going to need when we're talking about rotation about the center of gravity. And so some of the things we need to understand is there are common mass moments of inertia. These are on the back of our textbook, but these are some common ones, and after a while I believe you should have these committed to memory. But the moment of inertia of a disk is 1/2 mr squared, of a ring, where all of the mass is concentrated on the outside of the round shape, is mr squared. A ball or sphere is 2/5 mr squared, and a rod or stick is 1/12 ml squared. The other thing is that there's a concept called the radius of gyration, which takes out the mass of the moment of inertia. It allows us to deal with the shape only, and the radius of gyration is defined as the square root of I over m, such that if you're given the radius of gyration, you have to know the mass in order to find out the moment of inertia. So in many cases, k is given, something like this, and we'll have to square it and then multiply it by the mass in order to get the mass moment of inertia. And we'll have some examples of using that. Okay, so here's an example of 3 different shapes. All have the same mass, all excited by the same force times distance, and they have resulting 3 different angular accelerations. So first of all, here's a disk, and we're going to wind a string around the outside. We're going to pull it with a force of 2 newtons. Has a radius of 0.3. We're going to say that the disk has a mass of 5 kilograms, and all I have to do is find the mass moment of inertia. I'm going to say that the mass moment of inertia of a disk is 1/2 mr squared, and then look at our moments. Some of the moments about our point center of gravity is equal to Ig alpha. And I can find that, and the moment is going to be the force times the distance, Fd. So I can find that the alpha is equal to F times d over 1/2 mr squared. And plugging in those numbers, I can get 2.67 radians per second squared would be my alpha. All right, here's a different shape. This is a ring where all the mass is concentrated on the outside, and we know we'll soon learn to use the moment of inertia of a ring is mr squared. In other words, it's twice as much as if the same mass is evenly distributed over the whole disk. Do the same sort of thing, we find that the angular acceleration is 1.33. And here's our third consideration. We're going to say that we have our mass evenly distributed throughout a stick or a rod, same kind of force times distance. And we're going to say that the mass moment of inertia of a bar is 1/12 ml squared. Do the same kind of thing, and we find that our angular acceleration is 4. Wow, that's a lot more than either of the other 2 examples. Well, we'll find out that it is much easier to accelerate the mass of a stick than it is to accelerate the mass of a ring or of a hoop, or a ring or a disc. Okay, again, we'll use those more later. Here are 4 types of problems I want us to address in this video. First of all, we'll call this just simple rotation of a singular disk with a singular force or a moment. That's pretty simple. Here's a couple of masses, round masses, that are going to be accelerating in sort of a systems approach. Here's some friction where we got something going on here, and there may be some friction slowing down a rotating cylinder. And then finally, where 2 masses are connected with strings. All right. First of all, let's talk about some angular acceleration concepts, which we should remember. But let's say that we have a disk rotating about its center, given with some moment perhaps, and we know that there is going to be some angular acceleration that will occur, some alpha. Well, if we recall then, the tangential acceleration, A tangential is equal to R alpha. And that's going to be, of course, the same regardless of where we're at on the outside of the disk. All points on the outside of the disk will have some R alpha. If there's some point on the inside, it will have a different R alpha. It'll have, depending on the distance away from there. And if it's rolling without slipping, going along here, it's going to, and if it's got some alpha, means it's going in, being accelerated in this direction for some reason, we know that the acceleration of the center is also equal R alpha. All right, so we've got R alpha whether it's rolling without slipping or whether it's being accelerated by some moment. So those are things that we need to keep track of. The other thing is that we should remember that there is an R alpha profile, if you will, that at the top, if the middle is going at R alpha, the top is going to be A tangential is going to be 2 R alpha, such that there's a R alpha profile, a tangential profile that looks something like that, whereas at the bottom there is no R alpha. Of course, we remember that there's an R omega squared based on the omega, which is always pointing in, and that will always be there regardless of whether there's an alpha or not. Okay. With that, let's start our first type of problem. Here we have a simple round thing being supported by a couple of rollers, and we're going to pull on this. It looks like it's a spool that has a cable wound around the inside of the spool, kind of like we did in class. We're going to pull this with 300 newtons, and it's just going to rotate in place. We're trying to find the we have to find the alpha, and then we have to find some time that it takes to unwind a particular amount of cable. In almost all these problems, the main objective is to find alpha, and then we can apply the alpha that we discover in various ways. All right, so the first thing, let's find out what our mass moment of inertia is. It's given in the problem is that it has a centroidal radius of gyration of k is equal to 1.2. So we know that mass moment of inertia is equal to mk squared. It's got a 600 kilogram right there, 600 kilogram mass, so I can find out the mass moment of inertia by mk squared is 864. Again, simply the angle, or the alpha, then is just equal to the moment times, or moment is equal to Ig alpha. Now here's where some trick, or not tricks really, it's just recognition of what's going on. What is the moment about the center of G, or center of gravity, about O? It's very important, I guess, to understand is that the moment is going to be this tangential force times the radius. It's always going to be the tangential force always comes off, or the force always of an unwinding spool like this always comes off at a tangent, and the torque or the moment is always going to be that force times this radius. Don't get confused by trying to do some sort of sine, cosine components, trying to find lever arms and things like that. That'll really give you a lot of unnecessary work. All you have to do is just recognize that it comes off at a tangent, find out that radius, and that's always going to be the moment like that. All right, so if I do that, then I just got 300, and the radius at this point is 0.8, and I find that the alpha is equal to 2.2778. All right, once I find alpha, then I can find out the rest of the situation that I need. It says how much time is going to take to unwind 5 meters of cable, and you can see how I've done that, and you can do a screen print and figure out how I did that. But basically, 5 meters of cable is equal to r theta. R is point that. I find out how many radians are in 5 meters, and recognize that this is a constant force. Therefore, it's a constant acceleration, so that theta is 1/2 alpha t squared is going to be my governing equation, and you get 6.7 seconds. Okay, the next type of problem is a friction problem, and in this case what we've got is a wheel that's rotating. It's rotating at 40 radians per second before it actually touches down. What we're trying to do then, it's attached to this arm, it's rotating at 40 radians per second, then it touches down, and there's going to be some friction, and it's going to slow it down to a stop, and we want to find out how long that takes. So first of all, we need to draw all the forces on our free body diagram, and I've made a little bit of a larger picture here. So I'm going to say that this is going to be my normal force at C. I'm going to have an mg coming down into the arm. It says that the arm here is actually massless, but the wheel itself has an mg. So I'm going to draw my mg like that. If it's rotating in this direction, I know that there's going to be an alpha in this direction because the force of friction is resisting that. If the force of friction, or if it's slipping, then the force of friction is going to be equal to mu normal. In this case, it's going to be the normal force of C. Then lastly, we have a reaction over here at A, the support. So I'm going to draw my AX and AY, like that. All right, now I have all those pieces on the free body diagram. Let's do some equations. Again, what we're trying to find is how long does it take. In order to find out how long does it take to stop, we need to find alpha. All right, so let's do all of our equations that we know. Some of the forces in the x is mass times acceleration in the x. Well, this whole system is not accelerating to the left or the right, so that's equal to 0. So I can say that the only forces I have are mu c going in the positive direction, ax going in the negative direction. That has to be equal to 0. How about in the y direction? Here are all my y forces. I got a c, got an mg, got an ay. Again, it's not accelerating or decelerating or changing any position in the y. So therefore, the sum of the forces in the y have to be equal to 0. And I put all those in there, and I can get ay minus mg plus c is equal to 0. Now, the next thing is to recognize that this bar here is a two-force member. You can see that it's not straight, but it still acts just like we did in statics, that the line of action has to be equal to, or has to be along that straight line. All right. So once I find that, or once I recognize that that's a two-force member, then I can find out the relationships between AY and AX, just like we did in statics. And I do it like this, or I can do it like this, and you should do it the way you feel good. You can find the angle here, you can do sines and cosines, or you can use the ratio method and say that AY is 2.3 as AX is 2.4. When I do that, I can substitute that into this equation back up here. And I can see that AY is equal to 3/4 AX minus mg plus c is equal to 0. Now I have a two equations, two unknowns situation. I can plug this piece back into here, and I can solve for c is equal to, my normal reaction at c is 178.36. All right, now that I have the normal force, I can use a moment equation. And so I'm going to sum the moments about G, or about B, whatever, the moment or the center of gravity of the wheel. And I'm going to say that that's equal to IG alpha. We define a positive going counterclockwise. Again, it doesn't really matter so much, but you can define either way as positive for your convenience. But in this case, I have all the forces except for mu c go through B. In other words, because that's a two-force member, that goes through B, mg goes through B, c goes through B, so the only thing I've got is mu c times my radius. That's going to be the moment about G. So I got mu c times the radius, 0.2, is equal to my IG. My IG is given in the problem that let's see, where is it? It says that it has a radius of gyration of 0.15 and a mass of 25. So mass moment of inertia is mk squared, so I've just plugged that in. Mk squared alpha, and I can multiply all those things out and I get alpha is equal to 31.7 radians per second squared. Once I have my alpha, now I can go back and find out what the time it takes to slow down. And again, we can recognize this as a constant acceleration scenario, where we can say that omega, final omega, which is 0, is equal to our initial omega plus our alpha times time. And in this case, alpha is going in the opposite direction of omega, so one of these has to be a negative sign, and I can find that time is equal to 1.26 seconds. Okay, it's real important now to understand that this is not a statics problem, and many people try to treat this as a statics problem and try to find C in a statics way. So let's just again look at our free body diagram. If you would have drawn this as a statics problem and you just said, oh, I really don't want to solve for AY and AX, so I'm going to sum moments about AY and AX, or some moments about A. If I do that, and I could say that there's an mg times this radius, or times this distance, a c times this distance, and a mu c times this distance, and I could say that that's equal to 0. But that would be incorrect. And if you try to do this, you get mg times the distance, and you'd solve for c as 150.92. And that is not the right answer. So this is not a statics problem. Don't try to treat this free body diagram as a statics problem. Another way to think about it is that if you were to have drawn again, recognizing this as a two-force member and plugging this number in here, or plugging this projection of these two forces in there and say that AB goes through there, if you sum moments about B, then you got AB going through 0, or through B, mg and c, and again, mu c would be going in this direction. But if you were to treat this like a statics problem, you'd say sum of the moments about any point is equal to 0. But clearly that's not the case, because if you sum the moments about B and say that it's equal to 0, then you'd say that mu c is equal to 0, but that is not the case. So anyway, just be careful about how you set up your problem. Make sure that, that you don't treat it like a statics problem. Okay, the next thing is to talk about systems, and there are various types of systems we'll encounter, but here's a couple of fairly easy examples to deal with. But here we have a couple of gears, and one gear is being excited by a moment, and this one is obviously is going to respond because of that moment. If as we did before, the gears didn't have any mass, but in this case they do have mass, so they have mass moment of inertia. We have to figure out how our alphas will be affected by those masses. But the thing to keep in mind is trying to do a systems approach basically doesn't work. And what I mean by systems is treating both gears in one equation. You have to set these up as two free body diagrams and do it separately, if you will. So let's look at our first gear. I'm going to draw a free body diagram of the first gear. I'm going to say that sum of the moments about C is equal to IC alpha. I got a moment being driven, and I'm going to have a resisting force at the end where there's an interface between the two gears. This one's going to be excited by a force pushing it down. That force has to be transferred equal opposite back to this gear. So this is the force that resists this acceleration as well as the mass moment of inertia. So if I look at the total look at this gear, I'll just say sum of the moments about C is equal to IC alpha. I got that moment minus this force times the distance is equal to I1 alpha 1. Back over here then, makes this one go is this one has that same force, again equal opposite force times its radius, and sum of the moments about D is equal to ID alpha, force times radius is equal to I2 alpha 2. Recognizing those two forces are equal, and I can see that the moment is equal to I1 alpha 1 from this side, and then I'll bring that one to the other side of the equation, plus I2 alpha 2, and then the ratio of the radii. You can also need to recognize that from previous work we know that alpha 1 R1 is equal to alpha 2 R2. Using those two, using this identity into this type of analysis, you can solve for alpha 1 or alpha 2 as needed. And then after you find the alphas, then you can solve for omegas or times or whatever else you're looking for. There may be some integration involved. In this case, it looks like there's an exponential in there that you might have to integrate. But this is kind of the way you set those things up. And the last piece I want to visit about is the systems approach where we have a pulley and some masses. In this case, again, a systems approach does not work very well, and the reason is because just like we did in chapter, whatever it was, chapter 13, I believe, when we tried to do F equals ma with systems, there's just some conditions where you have to be cautious. In this case, we can't really do a systems approach because we now have a system or a pulley with mass instead of a massless pulley. So the way we have to do this is break up three free body diagrams of each piece, and define positive acceleration for all the masses. So I'm going to say that this is going to be positive for this guy. I'm going to say this one's going to be alpha positive going in this direction, and this is going to be positive accelerating down for the cylinder here. So three separate free body diagrams. This one has a mass of 15 kilograms, and I know that it's getting accelerated by a tension in that cable. The tension, if I look at the free body diagram of the pulley now, I have a tension on one side and a tension on the other side. Now, in all previous work, we said that those tensions are going to be equal to the same value. And now they are not, because the mass of the pulley has to be taken into consideration. We have different tensions on the two sides of the pulleys that we have to analyze. But regardless, we know that there's going to be a tension there and a tension there, and it's going to have some angular acceleration going in this direction. So this is T2 on that side of the pulley. And if I draw the free body diagram of this of the cylinder, I know it has a mass T2 and an mg going down. All right, so again, 3 free body diagrams. I need 3 equations of motion. So I'm going to say that from the forces in the positive is mass times acceleration in the positive. And I get an expression for T1. Sum of the moments about G, or O, I guess, is equal to Ig alpha. And I say that this is positive going in this direction, so that's positive T2 minus T1 times the radius is equal to 1/2 mr squared alpha. In this case, the disc, or the pulley, is being modeled as a disc. That's what it says right there in the drawing. So that my Ig is 1/2 mr squared alpha. Over here, then I get sum of the forces in the positive is equal to mass times acceleration in the positive. If I define positives down, then I have positive mg minus T2 is equal to ma downward. And I can put my numbers in there. All right, the last thing to recognize is that, as I did just a little bit ago, we have an alpha going in this direction. There's a tangential acceleration that is the same on all points on the outside of the pulley, and that A tangential is equal to R alpha. Therefore, alpha is equal to A tangential over R. A tangential over R is the same A as it is everywhere else in our system. So I plug that into our equation, and I can get an expression for putting these into there, putting that into there, putting this into there. I can get an expression for this where A tangential or A positive is the only unknown, and I can solve that for acceleration as 5.232. Once I have acceleration, then I can go back and solve for whatever else it's asking for. In this case, it's trying to find the velocity after it's traveled down 2 meters, and again, that's a constant acceleration equation. So I'm going to say that v is equal to, or v squared is equal to v sub 0 squared plus 2as, and we're talking about one of the masses here, probably the cylinder, and I can find that it is traveling at 4.57 meters per second after it drops those 2 meters, I guess. All right, well, I hope that is helpful in your studies.